Hey everyone, so sorry I can't make it to recitation today. Um, I'm sick, so I wanted to give you guys a little video just so y'all can be prepared for, you know, the exam and things like that. Um, so I'm going to go ahead and go through a problem with you. So the problem statement goes as such: a sinusoidal wave is traveling on a string with a speed of 40 centimeters per second. The displacement of the particles of the string uh, are 10 centimeters. Oh, I'm sorry. The displacement of the particles of the string at an x location of 10 centimeters varies with time according to y is equal to 5 centimeters sine of 1 plus 4 times time. The linear density of the string is 4 grams per centimeter. What are A, the frequency, B, the wavelength of the wave, and then if the wave equation is of the form y equals to xt, ym sine kx plus or minus wt, what are ym, k, and w? So the first thing that we're going to do is just look at this form of the equation. So one of the things that might be a little scary to look at is y as a function of x and t. It's a function of two variables at the same time. We're usually used to seeing just single variable dependence, so like y of x or y of t alone, but with waves we end up having two variables at the same time. Ym is called the amplitude of the wave. Inside of the argument of sine, k is called the wave number, and that's equal to 2 pi over lambda, and it has units of 1 over meters. And then W is called the angular frequency, which is equal to 2 pi times frequency, and its units are radians per second. So let's look at the equation they give us. I've just copied it down right here, just exactly as the problem statement says. And we can see that the amplitude using this formula of the equation is just 5 centimeters. There's something funky going on here, but we see 4 times t, that's the same as w times t. So that means that the angular velocity of the wave is going to be equal to 2 pi f, and it's also going to be equal to 4. And so radians per second. And so if we want to calculate the frequency, we'd be able to calculate that as 4 over 2 pi hertz, which are the units of frequency. Now, right now, the problem is not asking us for an amplitude. However, if it does, I would strongly recommend converting to SI units. Notice how it says 5 centimeters. We would convert that to meters. So the displacement here is equal to 10 centimeters. And so let me just correct a little statement I had there. It's not just 10, but it's 10 centimeters. And what that means is that this term right here is equal to kx. All they've done is they just plugged in x equals to 10, and now it's a constant. And so the way that we represent that on the left-hand side is that y as a function of x equals to 10 and t is going to be equal to what's given to us on the right-hand side as part of the problem. And so what we have to do in problems like these is sort of interpret the equation of a wave function and try to piece back things from this, using this general template about what's happening to the function itself. So how are we going to do that here? We know that 1.0 is a constant equal to kx, and that's going to be k of x multiplied by 10 times 10 to the negative 2 meters. And all this is 10 centimeters turned into meters. And then if we're going to go ahead and set that equal to 1.0. And what we're going to do now is just multiply both sides here by lambda to solve for lambda, which is our wavelength. And so our answer is going to be 2 pi times 10 to the negative 2 meters. Now, the other parts of the problem, we're not asking us for an amplitude, but I wrote that down anyway here. So that's going to be 5 centimeters or 5 times 10 to the negative 2 meters. I would always encourage you folks to use SI units whenever possible and leave the answer in that form. Now, they're asking us for K, and we know now that K times 10 to the negative 2 meters is equal to 1. And that means that the solution here is going to be 1 over 10 times 10 to the negative 2, 1 over meters. Now, if you get confused about the units of K or W, remember that the argument of the sine function has to be dimensionless. So if X is in meters, K has to be in 1 over meters to cancel it out. If T is in seconds, W has to be in 1 over seconds in order to have the quantity maintain lack of dimensionality. One of the things that's really interesting about this is when we get into computing W. Now, we can read the W, using our template just from the equation that's given to us in the problem, and that's going to be equal to 4 radians per second. But another thing to understand is that radians are dimensionless quantities themselves. And the reason behind that is because radians are ratios of arc length to the radius of a circle, which means that if we were using SI units, arc length would be in meters and radius would also be in meters. And so at the end of the day, radians are completely dimensionless. And as far as SI unit analysis, they can just be treated as one. But we say radians just to let us know that we're using, this dimensionless quantity to measure the angle in our problem. So I hope that helps you folks understand a little bit about radians and the concept of finding units inside the argument of these sinusoidal functions. That's it for our recitation. Thank you so much, and goodbye.